Hi, good morning, everybody. So in the last class, we looked at last couple of classes. We looked at a few features of mathematical preliminaries. We looked at some linear algebra results and the idea of differentiating a multivariate function, then which can be used for optimization. Right, probability stuff will return to it when we come to that specific topic. So there is a certain topic in clustering, so where we'll build some PDFs and model the data. So there, in that context, we'll get back to probability. So this class we'll be looking at data because this course is about data. That is, how do you represent data? How do you process data? So we'll look at how do you represent data and how do you visualize data. That is what we'll see in a couple of classes. So a data set is a collection of data objects, right? And data is often structured in the form of a data object. So data object also goes by many names depending upon the context. You can call it a record. So if you look at a spreadsheet, for example, let us say you have data of all the marks of a bunch of students in a class, right, or in a program. Right? Typically, the student names will be in the first column, and each row will have maybe the student's name in the first column, and after that, all the marks of the student or grades of the student in various courses. So each row becomes a record. So that's a data object. So similarly, a point in n-dimensional space, right, can be data object. So you can present a data object as a point in n-dimensional space, which is also a vector because vector is an ordered set of numbers. It can also be called a pattern, again, depending upon the context. An event, because when an event occurs, right, maybe you record a bunch of things at that event, at that time point. All right, so that's also like a vector or a data object. A case, a sample, right, an observation, okay, or an entity. So a simple way from a programmatic point of view, a simple way to think of a data object is a data structure. A data structure is a nice programmatic realization of a data object, which can have very composite things inside it. So you can have integers and floating points. You can have other data structures inside a data structure. You can have matrices, 2D arrays, 1D arrays, strings, right? So you can have all sorts of things within data object. So it's a collection of a bunch of data. That's what data object is. It can have very simple structure like a vector, just a row of numbers, or it can have more complicated structure like what you have in a data structure or an entity, right? But that's what we'll have to define, and we'll be using these kinds of data objects. In this course, for the most part, we'll be dealing with vectors. When you say data point or data object, we mean vectors. So a data object is represented by a set of attributes. An attribute is a property or a characteristic of that object. So this terminology might look a bit confusing now, but as we go deep into the course, you will feel that you'll see that depending upon the context, it's just common sense. What the terms mean is just common sense. But this is the kind of a formal terminology that people give. Now, attributes can be qualitative, and or quantitative. And within qualitative, there are two categories. One is nominal. That is just a name. It's a label, right, or a string. So, for example, pin codes. So, although pin codes are numbers, right, with 6-digit numbers or whatever, 5-digit numbers, they're not numerical values. In the sense, you cannot add up two pin codes and get a new pin code. It doesn't make any sense. And it's like an ID number. So you cannot perform mathematical operations on that number. It's just like just a symbol, just like an ID. So our eye color. So eye color is a qualitative thing. You cannot perform operations. You cannot say which is bigger, which is smaller, is it equal. You cannot add up colors, things like that. So that is the first subcategory of qualitative. Then you have ordinal, which is something in between, completely like qualitative, like nominal, and completely quantitative, like numerical. So in an ordinal case, here again you have labels, and they are essentially qualitative, but there can be an ordering among them. Like for example, good, better, best. You cannot put numbers on it, but you can see that conceptually, good is less than, better is less than, best. So these are called ordinal type of qualitative attributes. And then you have quantitative attributes which are simple. These are real numbers or integers, which is subcategory. So there's a numerical value, like for example, temperature or pH.
Sir,
Yeah,
what's
please.
the difference between ordinal and like nominal? Like I couldn't get what's exactly
Ordinal
ordinal.
and nominal.
Yeah,
Ordinal and nominal.
like I couldn't get exactly what is ordinal. Like,
No,
could you explain it
ordinal
once?
is also, see, it's a subcategory of a qualitative attribute, right? It is a label, a qualifier, but thing is, you cannot put a number on it. Okay, so for example, if you look at nominal, it's a label, and you cannot do any operations with it. It's just a symbol. Even pin code, which is a number, it's still not a numerical thing because you cannot perform mathematical operations. You cannot say, verify inequality, things like that. Ordinal is something slightly more than that. I can put them in an order. Good, for example, is less than, better, less than, best, right? Or white, gray, and black. There is an ordering. Although you cannot put a number on it, it is still qualitative, but within that there is an ordering. Whereas among pin codes, you cannot have any order. Or ID numbers, you cannot. Well, okay, ID numbers, yeah. If you there is can be serial order, depends on what the IDs are. Or eye color cannot have any order. Or names of people, right? They are also attributes, but they are not purely nominal. You cannot do equal to, less than, all that stuff. Ordinal is slightly more than that, right? Is there can be an ordering, intrinsic ordering among those labels, like good, better, best is an example. Is it
Sir,
clear now?
is there any example of ordinal data?
So
Sir, is there any example of ordinal data?
this is good, better, best is an example. Or how cold, how warm, cold, freezing, cold, lukewarm, warm, hot, blazing, something like that. Suppose I have a bunch of properties like that. These are attributes. Suppose I use them to describe weather, climate, right? So if I have such attributes, I can put them in order. Beyond that, I cannot put a number. I mean, what is cold? How cold is cold? I cannot put a temperature value by itself unless I make define a convention. By intrinsically, it doesn't carry any numerical value with it, right? Warm is how warm is warm, right? But still, even though there is, you cannot put a automatically cannot put a numerical value with a numerical value. There is still conceptually an ordering among those concepts, right? There are such situations. You can give many such examples. So, so even your, so for example, very often these days, even grades, right? Uh, so when we give recall letters, that's the best example familiar to your case. So in recall letters, we say, okay, how do you rate this candidate? Outstanding, excellent, very good, good, average. What is this? Can I put a number on it? Yeah, I can't. But there intrinsically there's an ordering, right? And the decision is made based on that selection, that qualifier. So such cases, such attributes are called ordinals.
Sure. So can we say categorical data to ordinal data?
No,
Like
not all
if
categorical data is ordinal because there is no ordering among every kind of categorical data. Can you put
okay,
them in
sir.
a serial order?
Like if they satisfy some kind of property,
No, like
like
take
you
for example
mentioned.
different categories of animals: cats, dogs, lions, tigers. So how can you put them in order? Doesn't make any sense.
Oh yeah, sir.
It is like that. So certain categories can be put in an order. Certain categories cannot put in order because the idea of order cannot be imposed. It's meaningless. So when you can impose an order on them on these categories, you call it ordinals. This is a subcategory of qualitative attributes. Is it clear?
Yes, sir. Got it, sir.
Okay, great. So now among quantitative, again, there are categories. Broad categories are discrete and continuous. Within discrete, you can have binary or even integers. And then there is continuous, the real numbers. But the thing is, whenever you represent anything in a computer, because data is not something that's out there in the world, it's there on the computer, right? So then it becomes automatically discrete. But continuous, conceptually, you need the continuous as a data attribute, but that mathematically it exists, but In a computerization, there is only discrete. Now, characteristics of data sets, especially if you look at only purely numerical data sets like vectors, right? One of the things is dimensionality. So some data objects can have lots of attributes. Then you say that they have high, the number of attributes is a dimension, right? They have, when you say large, when there are a large number of attributes, you say that the data object has high dimensionality. Now, high dimensionality is a problem because, so what happens is if you, let me take an example. Suppose I have a two-dimensional space. So let me change color. Now, suppose I take a one-dimensional space. Okay, I have a unit interval. Now I'm taking some discrete data in this. So I say I have, 10 points in the unit interval. So, but if I now if I have to sample at the same resolution a two-dimensional space, I have 10 points in this axis, 10 points in this axis, right? So the total number of different points I get will be, so here it is only 10. So my n is 10. In this case, n is 10 times 10. Okay, and so on. So here, so similarly, if it is 3D data, then n becomes 10 cube. So in general, for d-dimensional data, right, if I have to sample it at certain sampling rate, here I'm taking it as 10, that's a 10 per unit interval, then the number of points I need to uniformly fill the space will be 10 power d. This is just a simple calculation to convey the idea that if I have high dimensions, and very often I want the data to completely fill the relevant part of the input space. So that's how you can represent the phenomenon or the process. So if you have to do that, and if you have high dimensions, the data requirement grows very rapidly, grows exponentially with the dimensionality, so that's D. So that is called the curse of dimensionality. So high dimensions are not good and they're not desirable. But if you have a lot of high dimensional data, then there are ways of actually reducing the dimension. There are ways of transforming that space into a lower dimensional space, at the same time preserving some properties. Okay, so that such methods are called dimensionality reduction methods. We'll look at an important method like that called the PCA. Okay, another example is a self-organizing map or SOM. So we'll look at them, some of these things later. So another property of data sets is sparsity. So very often in some data sets, only a small number of attributes are non-zero, everything else is zero. So take, for example, image. So suppose you look at a pattern recognition problem or image pattern recognition problem. So if I'm recognizing faces, right, if I have grayscale images, then the entire face picture has some color or some variation of intensity and all that. But suppose I am representing characters. Okay, so I have, these are character images, right? And you have to pass it through some classifier and you have to classify them. Just look at this picture. So if this is, let's say, I don't know, some 30 by 30 array, within that only a small number of pixels are dark. Everything else is white. All the entire background is white. That means among these 900 pixels, maybe about 50 pixels are on, that is number equal to 1. All other background pixels are zeros, right? And this is the nature of the data. Generally, when you take character data, the only a few pixels will be high and all the other pixels will be low, right? In such data sets, you say that they have a high sparsity. They are sparse data. Only a small fraction of attributes are non-zero. So another property of data sets is resolution. So this is particularly relevant if you are looking at continuous quantities, right? And so continuous quantities exist mathematically, but when you have to represent them in a computer, you have to discretize them. You have to sample, right? The continuous variable, no matter what how you store. So that when this conversion from continuous to discrete gives rise to the concept of resolution. Okay, so for example, marks actually it's a continuous variable from 0 to 100, let us say. But when you type it in your spreadsheet, you're not going to say I got 83.674532. It's not a transcendental number or something. So you will stop at 2 decimals. So when you discretize, you have the concept of resolution. And you have to define based on the problem how much resolution you need or you can afford. Then types of data sets, there are record data, graph data, order data. Let's look at some of this stuff. So record data is basically a matrix. Like what you have in your spreadsheets is a simple example of record data. It's a matrix, and even documents can be sometimes represented as a matrix by following this interesting, presentation. So document is a bunch of words, right? A sequence of words. But so you cannot, it's not obvious how you can put it in a matrix form. So what they do is, this kind of presentation is useful when you want to analyze data, analyze documents, classify documents, right? Suppose you want all possible documents on cricket, right, in the internet, right? How will you search for it? You have to take some keywords that represent cricket, like team, coach, ball, etc. Something square, game, score, game, and so on and so forth. This is not particularly cricket, but anyway. So you can think of some keywords correspond to that sport. Now you can represent each document with respect to those keywords in terms of the number of occurrences of that keyword. So document 1 has 3 occurrences of the word team, no occurrence of the word coach, has 5 occurrences of the word play, and so on and so forth. Okay, suppose a document has all these words occurring with very low frequency or not occurring at all, then it's probably not a sports document, right? Similarly, okay, so this set of numbers, which represent the number of occurrences of these particular keywords, it gives a very nice profile of the document with respect to that class of documents. So you are looking, you're basically looking at documents with the lenses of certain keywords which represent certain topic, right? So like that, you can even express a document as a vector. And these are the kinds of representation that you use, for example, to classify documents, to cluster documents, and compare documents. How close is a given document to somebody else? Even things like plagiarism check involves these kinds of calculations. Okay, we'll see that later. So then there is something called market basket data. So that is, suppose you go to grocery stores, right? You go to shopping center, or you buy something, and people want to profile you, right? What kind of things do you generally buy? So it'll be nice if the storekeeper knows exactly what do you buy. Suppose you have a habit of buying like Sprite. Every week you will buy 1 liter bottle of Sprite. It'll be nice whenever you go to the counter, right, next time. That guy will ask you proactively, sir, ma'am, do you want to have your Sprite bottle today? Right. So like that, how do you get that kind of information? So the grocery store might have like some 10,000 different items. If you look at a large superstore, a supermarket, right? So then among them, you will be buying only like maybe at any given time 30, 40 items, right? So in that huge vector of 10,000 slots or 10,000 numbers, you count the number of items that you have bought, right, in a given category, and you only fill those slots, right? And that vector is called a market basket representation. Okay, so if person I buys, 1 bread, 1 Coke, and 1 milk, right? That means in the 10,000 dimension vector, right? You turn the entry for the bread category is 1, entry for Coke is 1, entry for milk is 1. That vector represents what you have bought. So those kinds of things also can be used to to cluster, to group the customers into certain categories, and which kind of customers come at which time of the day or which season. All this can be used to decide and how do you stock your whatever you manage your inventory and things like that. Then you have graph data, or sorry, network data. So best example for a graph is internet, which is of course a very big network. Then you also have in biology, in biotechnology, you have signaling networks, have different molecules acting on other molecules, and so on. So this is an example. On the right side is a signaling network. Then you have molecular structures, right? Right, which is also a graph. Okay, so I'm not a big chemistry fan, but this is the kind of I know the molecular structure of water. Okay, so I can try that. So then you have ordered data. So data where there is intrinsic order. Simple thing is example is signals or time series data, right? The stock values of Infosys company. Okay, so that's a time series data, or the sunspot activity, or Chennai temperature. That's a time series data. So or video data where there is an ordering, and so it doesn't have to be always time. Here, the what orders the data is time, right? But so here also typically what orders it is time. But multiple sequence data there's no time, but there is a sequentiality. Okay, going from one direction to another. Then you have image data. So point is, I mean, people just make this some categories because just to understand that there are different kinds of data. But when we look at the given context, I mean, it's just mostly common sense. All this terminology is just formalism, so don't worry too much about it. Now, when you have some data, okay, let us say you define data object, you have a lot of data coming from certain process or a system. Now, so the thing is, somebody asked me like, how is your class doing? How are students performing? If I give them like 150 numbers or whatever, 100 numbers, whatever is class time, and that will be overwhelming. So then they would say, no, I don't want so many numbers. Give me some kind of a summary of how your class is performing. So what do you do? Normally, a common sense thing would be to give class average, right? But then class average may not be sufficient because what is the best mark and what is the lowest mark? So then you have to give basically some kind of an average and max and min. So basically, to represent a body of data, right, and to summarize it, using a small number of properties, right, is a whole. So is the whole aim of statistical descriptions of data, and some of the standard properties that people use to represent like that to summarize data is median, max, min, quantiles, outliers, variance, etc., etc. So let us look at some of them. So first thing that you will do, think of, right, if you want to summarize data is the average or the mean value. Okay, so if n is the sample size, so then you just take, so if xi are your samples, right, you just take some of them and divide by n, and n notation is typically mu. Sometimes you also take weighted average, so then it becomes some weight times the mean value by the sum of all the weights. Then you have median value where the is a middle value if there are odd number of values. So you order all the numbers. After ordering, so exactly the middle value is the median if it is odd number, or the middle two values can be taken as a median, maybe the average of them. So if you take this example, right, the median interval is this interval. Then the mode is the most frequently occurring quantity in the data. And here again, you have multimodal data. I'll show you that in a second. So look at this example. So this graph gives you the distribution of some data. Let's say the class mark distribution of a given class. So here the distribution is symmetric. So there is this is the class average right here, right? And about that in both sides, the distribution is same, is symmetric. In such a situation, the mean, and this also happens to be the highest frequency point, right? Obviously, right? And it also happens with the median. So median means, like I said, if you order the data and then take the midpoint, that value is the median. Or if you take a continuous curve, a probability density curve, right? Then the point where the point where, right? If I take the entire area under the curve on one side, if it is half of the total area under the curve, so that's if the area under this curve is 0.5, then that is the median value. In this case, because of symmetry, that happens to be actually the point at the peak also. But if the curve is not, the PDF is not symmetric, like in this bottom two graphs, right, then the situation is different. The peak value is always the mode, because mode means highest frequency point, and this is the highest frequency point in this case. Then mean is here, and median is here. Okay, so in this case, it is called positively skewed. That means the mode is less than median, and median is less than mean. And if the skew is in a different opposite direction, then the ordering of these three quantities also is in the opposite direction. Mean is less than median is less than mode. And then you call it a negatively skewed distribution. And also, although in this is symmetric, this is positive skew, this is negative skew, these are all examples of unimodal distribution. That is, there's only a single peak. But if you have a curve like this, right? This is bimodal, okay, or trimodal. So there are multiple peaks, right? These are all unimodal, but there is a skew. Then let's look at dispersion of data. That is, how much is the spread? So you need mainly two things, right? What is the average or central tendency, the mean value, and how much is the variation around that? So these two notions are described by so many different things. Median, mode, they represent some kind of a central tendency. And quartiles and standard deviation, variance, and they all represent some notion of the spread. So if you look at quartiles, you order the numbers, right, from the first number to the last number. Let's say so from 0 to 100 or something like that. The last is 100, and then on this scale, there could be 10,000 points, but I'm just representing them on this scale. So now you take the point where you have 1/4 of the data covered. Okay, let us say so somewhere here. So I plot them like this. Okay, smallest point is plotted here, highest point is plotted here. So 1/4 of the points are covered, right, at this point. Half of the points are covered at this point. Let's say some 3/4 are covered at this point. Now this is called 25th percentile point. But this is your percentile, and this is how even some of your entrance exams scores are given, right? So this is 50th percentile, 75th percentile. So from 0 to 25th, this is called Q1, or the first quartile. From here to here is called second quartile. From here to here, it's called the the middle number between the smallest number and the median. So this is correct. So this is the let me solve. Okay, so this point is Q1. Okay, the median point, which is the 50th percentile, is Q2, and this point is Q3. Right? Okay, Q2 is the median. Third quartile is the middle value between the median and the highest value of the data set. Now, so Q1 gives some kind of a central tendency. Q1 and Q2 tell you something, some notion of this spread in either direction from the central tendency, and therefore the Q3 minus Q1 is similar to the idea of a standard deviation, but not exactly the same. This is called the interquartile range, Q3 minus Q1. So this 5 number, and then you have min value at one end, okay, and max value at the other end. So these 5 numbers, min, Q1, Q2, Q3, and max, and Q2 is nothing but median, right? So min, Q1, median, Q3, and max. These 5 numbers are called the 5-number summary, right, of a given data set. These are all one-dimensional data sets. So now these 5 numbers can be pictorially represented using something called a box plot. Okay, and this plot looks like this. So in the box plot, so these 5 numbers are represented by a box with what called whiskers. So draw the median and using a small vertical line, and then the Q1 is also marked by a vertical line. Q3 is also marked by a vertical line. Give it some height. Okay, it doesn't matter what exactly is the height. Then put all these 3 lines inside a box. This is the box part of the box plot. Then from this point onwards to the mean value, you draw only a straight line. You don't draw another box here like this. Okay, from this point onwards to the midpoint of this line to the max value, draw another straight line, horizontal line. Right, so this box and two whiskers on either direction, this whole thing is called a box plot. Now, why is it drawn like this? Why can't they just draw whole thing as one line and then put some markings? That also conveys same information. Okay, why have this change? Or put box completely throughout so that just one big long box with partitions. It look like a little train. So why not draw these nice pictures of trains, which is fun? So the answer to that is, when you draw a box plot, you are putting only the interval from Q3 to Q1 inside the box. Outside that, you are leaving it just as a straight line. Just to indicate that the majority of the mass of the data is between Q1 and Q3. Okay, to indicate that massiveness of the data, which is located from here to here, and to indicate that the amount of data outside beyond these ranges is somewhat sparse, somewhat less in its volume. Right, they want to indicate the central part using a box and the outside part using whiskers. So this gives an idea of the appeal and the need for visualizing data, right? Coming up with nice graphical visualizations of data, just to intuitively convey the idea of what the data is like, what data is about. You can always give some numbers, but numbers are abstract. Pictures are more concrete. They make the thing come alive. So box plot is already one preliminary example of the kinds of things people like to do to visually present data in a very intuitive fashion. So in box plot, the data is represented. It is summary of these 5 numbers, this 5-number summary. It's a pictorial representation of this 5-number summary. And it's represented by a box. The ends of the box are at the first and third quartiles. Okay, and the height of the box is the interquartile range, or IQR. The median is marked by a line within the box, and the two whiskers, two sides, they will go all the way from to min on one side, max on the other side. And in this, so you can define some kind of a threshold. Sorry, you can define some kind of threshold. So suppose the gap from median to Q1 will give you some notion of the spread on the lower side. Now suppose I define a threshold like some k times this gap. Okay, some k times this gap is considered to be the extreme limit of the data on the lower side. Right? I just define something, and then I say that anything beyond that is just an outlier. It's not. It's just a freak point. It's not supposed to be there. It doesn't even form part of this distribution. Right. Similarly, I take this gap, and I say take some some k times that, or some fraction of that, or some factor of that, and I say it doesn't have to go all the way to the max. Right. I define a threshold in terms of this, and I say anything beyond that to the right side is a freak. It is an outlier. So outlier, so determining that a given point is an outlier itself is a big subject. There's so many algorithms to define that, define that a given point is an outlier. This outlier mess up your these 5-number summaries. Any summary of the data set, right? First, you need to be careful not to take outliers. But typically, what people do is you first determine the summary, and then using the summary, you go back and determine what are the outliers and throw them out. Okay, so then let us look at kind of a classic probability distribution function, right, called the normal distribution curve. So this is what is also called the Gaussian distribution, right, given by. So I'll talk in more detail about this when we come to this probability topic later. So let us just call it a bell curve or a Gaussian or whatever. Mathematical definition I'll give later. So for a Gaussian, the mean is 0 and there is some standard deviation. So in this normalized form, the mean is 0. Or if you want the notation, mean is presented by mu, and standard deviation is sigma. Right, and so if you look at the area under the curve between the mean and one standard deviation. Okay, so that is sorry. So that is this. So that is 68%. So this is 1 sigma. And if you go to 2 sigma, right, and that gives you 95% of the area. So sorry, so that gives. Right, and if you go to 3 sigma, you get 99.7%. Right, and you might have heard of this 6 sigma, right? 6 sigma will be even, if you go to 6 sigma on either side, it will be much smaller. So that is used in the context of quality control. So the number of defective items when you produce something, the product, right? Number of defective products should be, or number of good ones, quality ones, should cover 6 sigma. That is 99.9999 some percentage of the product should be of proper quality. They should not be, you not reject them, right? So that is, so this it comes from this context, right? As you add more and more sigmas, you get bigger and more area is covered, right? Within that some mu plus or minus some k sigma. Okay, so 6 sigma is like generally very good. So you can associate, you can draw a box plot corresponding to the normal distribution like this. Because the normal distribution is symmetric, mean is same as the median. So this point, the peak point is also the median. And you take the IQR, right, as Q1 and Q3, right, and Q1 minus 1.5 times IQR you take as a minimum, because the Gaussian distribution goes all the way to minus infinity on one side and plus infinity on the other side. So obviously you cannot draw a box plot where the whiskers go up to plus infinity, minus infinity. It doesn't make any sense, right? So you take this IQR and so Q3 plus 1.5 times IQR is the upper limit. This is kind of a notional max, right, for the distribution. And the Q1 minus 1.5 times IQR is the notional minimum, right, of this distribution. So like this, you can associate a box plot with a normal distribution. Now you can draw box plot. So this box plot that we have seen until now is for one variable at one quantity, let's say x or xi. But suppose you have lots of quantities, right? And so in this case, on the plane, let's call this this x and this is y. So there are so many different variables all along the way. Okay, both in the x direction and y direction. So at every point for every variable, I can define a box plot. So you get a whole looks like a forest of box plots, right? And there such things are called 3D box plots. So a similar notion. So in the context of box plot, we talked about the IQR, interquartile range, which gives you an idea of spread of the data around the median. Is another notion of that kind is a variance, which is given by, so x is the sample value, mu is the mean, right? Sigma xi minus mu square, right, divided by 1 by n. This is called the variance. Sometimes people also use n minus 1, but when you have a large number of samples, right, that whether you use n or n minus 1 doesn't matter much. Okay, so right, you can show that this is equal to this. Okay. Now square root of this is sigma, which is called the standard deviation. So if you look at there are several ways of displaying the basic statistical summaries graphically. One of such methods that we have seen is box plot. The other representations or other ways of displaying data. One is a histogram, then you have quantile plot, then scatter plot. So let us look at some of them. Histogram is something that you might have seen in some other courses, or some of your lab course also might have introduced the notion of histogram. Histogram is basically this. If you have some data, right, varying over a range, so from, in this case, from 10,000 to 1 lakh or something like that. Divide that whole range into small bins, okay, and count the number of occurrences, number of data points which fall in each bin, and plot that value on the y-axis. So the number of occurrences, the frequency of that of the data points within that bin, you plot on the y-axis. Only thing is, instead of plotting it, if you want to just, you can plot it as a continuous curve, right, like that. But that's not a histogram. In a histogram, that y value is represented as a rectangle. Only then you call it histogram. Okay, so it will be a series of bars, a series of rectangles. Because that's a convention, that is a procedure, right? And that's called a histogram, and it is kind of an approximation of a PDF. So if you can draw a histogram with finer and finer resolution, and then continuously connect all the peaks, all the topmost points of all the rectangles, you get an underlying distribution, the PDF. So histogram is a very discrete representation of the underlying PDF. You can say that. No, histograms often tell more than a box plot, because look at these two histograms of some data. Right. In the first case, you can see that it has two peaks. There seems to be some kind of a bimodal distribution underlying the first data set. Kind of seems to be like bimodal. This one seems to be unimodal. Right. But when you look at histogram, you can make that out. But if you construct the corresponding box plot, you don't even try to see if it is unimodal or bimodal. Because in box plot, you just take the median value, you just take Q1, Q3, and then draw this. Right. And so in both cases, your box plots will look the same. You'll believe that in the center of the data, there's a lot of data, a lot of volume, and then on the peripheries, it has become sparse. Right, and because that is what the box plot assumes, and that's why you kind of force fit whatever be your summaries back into that form. But whereas when you plot it as a histogram, right, you can see the difference, and you can make out that here this is a bimodal and this is unimodal. And in this case, most of the mass of the data is in the center, and if you go to peripheries, it become more sparse, right? And that is why in this case the box plot is more suitable, more meaningful. Whereas in the first case, where it is actually bimodal, a box plot is not quite suitable. So histogram tells you more than what a box plot does. Then the quartile plot. So we already mentioned once this kind of representation. So basically, you take all your data, right, and order them, and plot it in the ascending order. So the smallest value, mean value is here, highest value is here. Okay, and it doesn't have to increase so uniformly. It can have lots of variations. But it has to be monotonic because it is ordered. And call the lowest point corresponding to 0 and highest point corresponding to 1, right? And so if that is the case, then take so basically these are the indices, right? The x-axis is basically indices. So indices of the data points, let's say they go from 1 to n, right? And then you convert that to a continuous variable from 0 to 1. If you do that, the 0.25 point will give you the first quartile. This gives you the percentile, obviously. All right. So this representation is called the quantile plot, because all these different quantile values which we calculated and kind of incorporated into the box plot, you can see all that right straight away in this plot. Then the other thing is a scatter plot, which basically tells you the relationship between two quantities. Okay, so so sometimes when you take two quantities, so the way we have been used to depicting the relationship between two quantities, x and y, is simply to draw a graph. But sometimes if you take x and y from some data set, these are observations, single observations, and plot the data, the data points may not nicely line up to form some kind of a curve or a graph, right? So sometimes when the data points are not even related, let us say I take this sunspot activity or Chennai weather and Infosys stocks, right? So this is Chennai weather Infosys stocks, right? Over a series of over a couple of months, every day I take that and plot it. It won't have any. I can't fit a nice curve going through it because the data will be all over the place. So trying to draw the express relationship between two quantities as a graph, it doesn't make sense all the time, right? You don't want to connect the dots because the dots cannot be connected. There's no underlying pattern. So in order to, without trying to force fit some kind of a graph, right, into the data, we just say, okay, let's not draw a graph connecting all the data points. Just let us plot the data points and see what they're like, what the picture tells you. Okay, let the data speak for itself. So with that intention, we make these scatter plots. We just look at how much data is scattered around some kind of underlying pattern. Okay, so that's a scatter plot. So I think next we'll talk about data visualization. I'll just quickly introduce it and we'll stop here. So some of these things that we have seen are also examples of data visualization. This is data visualization, right? So is this, and so is your simple right effort to draw the express relationship between y and x as a simple curve. Right? That's all data visualization. But thing is, when the data gets more and more complex, those kinds of simplistic data visualization tools may not be sufficient. So people come up with very innovative, very elaborate forms of visualization. And in fact, this whole problem is more sometimes is more like an art than a science, right? You can come with very innovative ways, and that becomes a kind of a some kind of a it's even patentable. I think I'm not very sure though. There's a lot of creativity that goes into these data visualization techniques. Why do you need to visualize data? Because you want to get an insight, right, into what it is about. So, for example, if you're studying protein structures, right, you can draw your Ramachandran plots and you can give, I don't know, all sorts of properties of the protein. But there's nothing like a 3D visualization of the protein in a virtual reality setup, right? You can go into it, you can actually touch various amino acids in the protein, with your glove. You can rotate it, you can walk inside the protein, you can walk on the protein. So, I mean, a good visualization, there is no substitute, right? So similarly for data, if the data is quite complex, good visualization can really give you an intuition into the nature of the data. So it gives a qualitative overview. You can search for patterns, trends, and so on, right? And you might find interesting regions and suitable parameters for further analysis. So I'll just take look at these two examples and we'll stop here. So for example, you want to visualize a spectrum, right? What is spectrum? The amount of energy present at various frequencies in a signal. So x-axis is frequency, y-axis is, let's say, the amplitude or energy present. I'll call it A. So let us say the energy is all present, not much in low frequency, it's all present in some band, after that it falls off. Now I give a picture like this. So this is good enough. But just see how they depict the spectrum like in a radiation. It's a solar radiation. Right? It's actually pretty interesting and it conveys a lot of meaning because the left part says how much energy is present in the UV part, or in the violet part. Right side says about red part, and so on and so forth. But and the intensity, how bright it is, tells you how much energy is there. How dull or dim it is, tells you how less is the energy. But the point is, other than that kind of fun aspect of it, why not just go with something like this? Why do you need this kind of elaborate construction? See, one important thing that this colorful depiction, in addition to the fact that it's colorful and nice looking, one important feature that this depiction brings out about the solar spectrum, which is very hard to bring out in this form, is look at these black lines, right? There are lots of these black lines in this depiction. So the black lines indicate the points where the frequency is missing in the solar radiation. So their energy is zero. and it's not so suppose even here energy is 0, right? But energy is 0 at very fine narrow bands. At that frequency, in a small band, energy is missing. So how do you depict that in this graph? You will have to make sharp cuts, okay, which looks very weird. You can't even read the graph. You make lots of such small sharp cuts in this graph. So you look at this, such an innovative way of depicting this kind of a strange data structure, right? The spectrum of the solar spectrum or spectrum of some radiation, which has lots of missing gaps. So similarly, microarray data. Okay, so that's again a 2D example of 2D visualization. Okay, so let us stop here. We'll look at some more complicated cases, and we'll look at the concept of similarity and all that, right? And the next class, that is tomorrow. Then tomorrow we'll also watch a video on how to make statistical visualization very interesting. It's almost entertaining. It's like watching a thriller, like a very some of these TV shows you binge watch, right? How do you present data in such an interesting fashion that the data tells a story, right? It's quite possible. I mean, so people who might think that might be thinking that the data analysis is all such a bore, right? You will change their view when they see this video. It's a TED talk by Hans Rosling. So we'll watch that along with a bunch of other things in next class tomorrow. So that's all for today.
Sir?
Yeah.
Could you tell me more about quantile data? Like how do we get that x-axis range between 0 to 1? Could you go
Sorry,
to on that
one
slide?
second. 1 second. Yeah. This quantile plot.
Yeah, sir. Like how do you get this range between 0 to 1? Oh,
Yeah. So let us
like
say
what?
I have 1,000 points, right? 1,000 values. Okay, and you order all the data, order all the 1,000 values, and simply you plot them. You plot. Sorry. Okay, you plot them like this, right, in ascending order. Now this is your first data point. This is your 1,000th data point. Okay. Now the same axis, I map it on to the unit interval where this end is 0, this end is 1. Okay, your capital N, which is the size of the data set, maps onto 1, and the first data point maps onto 0. Okay, so once these diamonds that you see here are the values of the data. This is some unit price, the cost of some product. Okay. So once you plot like this in ascending order, in this interval you take 0.25 on this, 0.5, 0.75. Okay, and so although I have drawn these vertical lines, you just connect the tops and draw it like a graph. Now 0.25 you extend and see where it cuts. 0.5 you see where it cuts. 0.5 will be your median point. This one will be your Q1 value. This is your Q3 value. So what you have used in the box plot, you can extract those numbers in a different way by drawing this quantile plot. Right? Is this clear now?
So like that thing I am asking, like how do we map that range between 0 to 1? Like sure, do we divide by
So
some value?
no. So okay. So when you're drawing a graph of all these 1,000 points, right? You have to draw it spatially, right? How do you draw this graph? When you draw this graph, I give you, let's say, 100 points, and I want you to draw this graph and mark them in the ascending order like this. You take some line, right, a horizontal line of some length, okay, and you pack all these numbers. You divide this into n parts. This line you divide into n parts, and you depict all these discrete points, right? Yes or no?
Sure, like you mean this x-axis is representing index, right? Like
Yeah, x is representing index, yes. So initially it represents index. Let us say this is 1, this is n. but you are plotting it on a certain line of certain length, right? When you draw a graph of this, then imagine that line, this length, this line of certain length is mapped
So
on.
there
Yeah,
might be a chance that we are not getting any linear line, right?
it's
Like
not a
we might get
line.
some
No,
random
no,
things
no, no,
like
no. No, this is not.
so.
This may not be. Doesn't have to be line. The points
Okay.
won't form a line normally, but it will form a monotonic curve because you ordered all these numbers, right? So it will be in ascending order. You have to put them in ascending order,
Okay,
right?
sir. I got it.
Yeah. Okay. So see you tomorrow.